Hi, Year 9, and welcome to another lesson of science with me, Mr. Ereaut. Today we're going to look at hydrocarbons. So this is a lesson 3 out of 4 of your crude oils topic. And so today we're going to look at hydrocarbons. Now, yesterday you looked at fractional distillation during yesterday's live lesson. So to start with, please, can you order these statements from 1 to 5 in the correct order for how fractional distillation works? Okay. The other thing on this slide that you can see over here on the right is your hydrocarbon names. So there's a number of different hydrocarbon names, so methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. So from 1 to 10, okay? You can also have methane, ethene, propene, butene, or methane, ethine, propine. So these are your hydrocarbon names. That's just kind of a generic general rule there for your hydrocarbon names, which I find quite helpful to remember. So you might want to pause and just note those down there. You'll learn about the differences in the 3 of those as well. But to start with, pause the video please and have a go at ordering these fractional distillation statements into the correct order. Okay, so let's check your answers. So first one, the crude oil is heated. Okay, all of that crude oil that's pulled out of the ground is then heated. Then number 2, it's then vaporized. Okay, some fractions of it remain as a thick liquid. Okay, so they don't turn to vapor. So they've obviously got a really high boiling point. Then C, those vapors then rise up through a column, your fractionating column. D, some of those vapors will condense, and they'll condense at different points once they meet their boiling point or their condensation point, because it's the same point. And then the last part, those fractions are then tapped off and purified into pure fractions of oils. So petrol and diesel and tar, for example, are all fractions of crude oil. So they're all contained within crude oil, but then you get them out when you fractionally distillate crude oil. Gosh, that was a mouthful. So on to today's lesson though, and we're going to look at what actually happens, what the properties are depending on those fractions. So you've learned about how we get the fractions, the fact that they've got different boiling points and they condense at different points. We're now going to have a look at what they actually mean, or why they fractionate at different points, or why they condense at different points. And it's to do with the size of the chains. So crude oil or hydrocarbons, they're formed of really long chains, or you can also have really short chains of carbon and hydrogen joined together. So we've got our short chains, like methane, for example, is obviously the shortest chain. And then we've got our long chains, things like tar, for example, is very viscous, and aeroplane fuel is also very viscous. It's got a really long chain. So that's the first thing. So size of our chain. So these chains get longer and longer and longer. So as you get longer chains, their boiling point actually increases. So as the chain gets longer and longer and longer, the boiling point gets higher and higher and higher. So these really long chains have a really high boiling point, which means they don't make it as far up the fractionating column as the short chains. Because the short chains have got really low boiling points, they condense at a lower temperature, which means they make it further up the fractionating column. So then we have volatility, so the tendency to turn into a gas. So our short chains are much more likely to turn into a gas than our longer chains, for example. Viscosity is how easily it flows. So short chains, think of them like water. They flow really easily, okay? While there's our long chains, think of them like honey, for example. So honey is a very, very viscous material, so it doesn't flow very easily. It's that gluggy kind of material. So our long chains are far more like honey. They're thick or viscous. And then last but not least, we've got flammability, so how easily it burns. So the shorter our chain is, the easier it burns. So our short chain molecules burn far easier than our long chain molecules. So you need to know those 5 points and 5 differences between short and long chains. So please write those down, and then once you've got that down, can you please try and answer these 2 questions? Why are longer chains more viscous, and why are shorter chains gases at room temperature? Think about what we've just talked about for the last 3 minutes, and have a go then, once you've got those points down, at answering those 2 questions. So pause the video now and answer those 2 questions. Okay, so let's go over the answers to our 2 questions. So longer hydrocarbon chains are more viscous because the chains get tangled and they make it harder for the molecule to flow past each other. Think about it like, I don't know if you've ever been fishing and you've got lots of fishing weights on different lines, they all get tangled. It's absolute chaos. All your phone wires, if you've got multiple phone wires in your pocket, they get tangled very, very easily and they are a pain in the neck. And then obviously you've got your smaller molecules, so they're really small. So think of it like a ball pit. They're tiny little balls, so they just flow over each other much easier because they're not really connected to many things, so they don't get tangled. And then second answer, why do the smaller molecules they have a gases more easily? It's because they've got a lower boiling point, and also because they have a weaker attraction to the neighboring molecules, so they're basically just attracted to themselves. All right, just like certain shallow people, like models, for example, are attracted to themselves. These smaller hydrocarbons are attracted to themselves and not the neighboring molecules, and therefore they find it much easier to become a gas because they've got much lower attraction to the surrounding molecules. So I'm going to show you this experiment in a minute. So I've got my fuel, and then I've got funnel, and then I should hopefully be, obviously got fuel, it's combusting, and then it's releasing gas, which then travels up into my funnel, and then goes through this funnel, and then into my lime water, and then at the top here. Okay, and then in the experiment, I'll talk about why I'm putting it into a funnel, why I'm putting it with cold water, and why I'm putting it through lime water.
So we're going to test combustion currently and see whether this is a complete combustion or an incomplete combustion. So what I've got here is ethanol. So ethanol, as you can see, it's C2H5OH, and that's how it's drawn there. Okay, so it's ethanol. So it's ethane with the O, which is the OH. So we're going to test this ethanol and see what happens. So we're going to light this, which is filled with ethanol, and then the gas is going to be sucked up here and then through and into here. And we'll talk about each section as it's running. So I'm going to light my gas burner here. As you can see, it's a nice flame. And I'm going to turn this tap on here. So the tap just creates suction. So what's happening is it's pulling oxygen from here all the way through this. So if I then turn this on here, it should be sucking the gas that is released, so the product, up through this tube, and then through this tube, and then through this tube here. And so if I run the tap, it should start that suction, hopefully. There we go, so we should be getting that suction running there, that's good. So as you can see, you get your bubbles. So the first thing here we've got is the flames going into here. So if we have an incomplete combustion, it will leave soot on this, which will be black. So soot is carbon, so pure carbon. Then we have this here. This is cobalt paper. So it's normally blue, but if you heat it, it goes white. So it's dehydrated. And so if we hydrate this cobalt paper, so if it has the presence of water, this cobalt paper should hopefully go blue. And then last but not least, if there's carbon dioxide being produced, this lime water will go cloudy. And as you can see, the lime water has started going cloudy here, which means that there is a presence of carbon dioxide. And this paper here, even though it's a bit hard to see around the edges, it's starting to go blue, which means that there is a presence of water vapor actually being in here. And then last but not least, if we look at this, it's got black around the edges, which means that there is carbon present. So it's an incomplete combustion because it's got carbon or soot here, so there's not enough oxygen.
So, I hope you enjoyed that experiment. I certainly enjoyed doing it. Now, I've got some questions for you on that experiment, which I hopefully discussed the answers. So, can you tell me, please, from what you just saw, write down the reactants and products of combustion. So, what were the reactants in that experiment, and what were the products? Then, can you try putting the reactants and the products into a word equation for me? And then, if you're feeling really tenacious and you think you can do it, have a go. Can you please then try and produce a balanced symbol equation using your word equation? Okay, so I hope you managed to do those, at least two of them, if not the third one. The third one is quite hard. So here we've got a complete combustion. So when you completely combust a hydrocarbon fuel in oxygen, you produce carbon dioxide and water, as you can see below in these two chemical equations. So how many moles of reactant and product can be seen in each equation? So if we firstly look at this, we've got our methane plus oxygen, so methane CH4 plus oxygen 2O2 forms carbon dioxide and water. So that's an answer for your previous slide. Not the methane, but the fact that they're producing carbon dioxide and water. Then how many moles of reactant and product can be seen in each equation? Well, in this one, we've got 1, 2, 3 moles here. And on this side, we've got 1, 2, 3 moles. On this one, 7, 8, 9. On this one, 6, 7, 8, 9, 10. So those are the moles from each reactants and products. So what did the lime water test prove in my experiment? If you said the presence of carbon dioxide, you are right. What was another product of combustion other than carbon dioxide? If you said water, you were correct, unless it's incomplete combustion, in which case we'll get to that in a second. Write a word equation now for propane burning. So propane plus what forms what plus what? Pause the video, have a go. If you wrote propane plus oxygen forms carbon dioxide and water, you are correct. So, got some more word equations here for you. Can you write the word equations for complete and incomplete combustion for the following hydrocarbons? Have a think, please. And if you can't come up with a complete combustion, have a think about whether it might be an incomplete combustion and why, because that's what we're about to go on to. So pause, have a go. What of these can you do from the previous learning earlier in this lesson? How many of these questions can you answer? Okay, so there's an animation that I'd like you to go watch. So can you go over to this link, please? It'll be on the PowerPoint if you download it. Otherwise, just type it in. Have a go, please, at looking at this animation. It's a bit slow, so you're going to have plenty of time to write down in your own words what is happening to the atoms during combustion. And then what is the symbol equation for this reaction? So have a go at those two questions, please. what is happening to the atoms during combustion. Write that down in your own words, and then also write down what is the symbol equation for that reaction. Pause the video, jump over, watch that one, and have a go at answering those two questions. Okay, so hopefully you answered those two questions. They were nice and easy. The video spells it out for you. So we're going to talk about incomplete combustion now. So before we were talking about complete combustion, so the same number of products as reactants in terms of atoms. You had enough oxygen, but not all the time is there enough oxygen for a reaction to occur. So in incomplete combustion, hydrocarbon can only be completely combusted if there's plenty of oxygen around. If there's not enough oxygen, the hydrocarbon will react with oxygen to produce carbon or carbon monoxide, both of which are not good. So what's the word equation then for an incomplete combustion reaction? Well, it's fuel plus oxygen will form either carbon, carbon monoxide, carbon dioxide, or other carbon oxides plus water. So it's almost the same reaction, except we're not forming carbon dioxide this time. We may be forming carbon or carbon monoxide if there isn't enough oxygen present. So carbon monoxide is a colorless poisonous gas that's no smell or taste. It's really bad. All right, that's why most of you should have a carbon monoxide alarm in your house. If not, I'd suggest you get one so that you know it, because you can't taste it, you can't smell it, but it can kill you. So it's also a flammable gas that's slightly less dense than air. So breathing it in can make you unwell. It can also kill you. So around 60 deaths from carbon monoxide poisoning in England and Wales. So it does happen because you can't smell it and you can't taste it. So carbon monoxide is this one up here. It's got one carbon and one oxygen. So how does it kill you, you might ask? Well, firstly, it enters your bloodstream and then mixes with the hemoglobin. So hemoglobin is the part of the red blood cells that carry oxygen around your body. Okay, which is why you need lots of oxygen, lots of iron in your diet, so that you've got lots of hemoglobin in your blood so that they can carry oxygen. So what it does is it mixes with that hemoglobin and forms this carbohexyhemoglobin. And then when that happens, the blood's no longer able to carry oxygen. And so then that's why you get sick. It's because your body's not able to get that oxygen to all of your cells, which is why you then die. So make sure you pause the video and get down what is carbon monoxide, why is it bad, okay? And then the other one is carbon, okay? You know carbon in terms of soot. So if you think about any fireplace or anywhere where there's lots of fire, and then you have a look at the walls of your fireplace or the chimney of it, it's always covered in that black soot. So that's because of incomplete combustion, so that carbon is not bonding with oxygen to form carbon dioxide, and so it leaves soot or carbon, which is what we saw on the funnel during the experiment earlier in this lesson. So, quick question check. So what does complete combustion mean? Good, I hope you've answered that. Remember, you need to be pausing and actually trying to answer these. So it's when something burns in lots of oxygen, okay? So you got complete combustion, something burns in lots of oxygen. So then what's it called when there's less oxygen or not enough oxygen for burning? If you said incomplete combustion, you are completely correct. And then name two products of incomplete combustion. I should have said carbon or soot and carbon monoxide. Mon means one, so one carbon and one oxygen. Okay, year 9. So depending on how much time you have left in the lesson, have a go firstly at these questions here, please. And then if you complete these and you still got some time in the lesson, please have a go at the next slide, which is 2 maths questions. So, the first question should be pretty easy for you, which is just draw a balanced simple equation of butane reacting with oxygen and forming carbon dioxide and water. That should be a pretty straightforward question. The next question, however, you probably won't know how to do, unfortunately, because we have not done that topic in chemistry yet. So don't worry too much about the second question. It's just in there for interest if you are interested in it. There's no worries at all because you won't actually know how to do it yet. So there you go. Those are the answer. The first one, you should know how to do A. All right, you should be able to get that balanced equation. The second one, you do not know how to do it. It's just there for interest's sake. And to remind me almost that we need to go back over this and teach you it. But we will get at that. That's a different chemistry topic for next year. Guys, I hope you enjoyed the lesson. As always, stay safe and see you in the next live lesson.